Okay, great. So before we start, I need to make an announcement. Remember last class we had the letter D. I need it back. So so D no longer represents the distance of a code. It is now free for claim. I will claim it in two different ways through the thing. Okay, good. So today we will see expander codes. These are going to be another family of positive rate, positive distance binary codes over 0. Last class we saw Reed-Solomon codes concatenated with a brute force searched code of smaller size. This is another family. These are the only two families we know. We do not know another way of getting good rate, good distance codes. And so every once in a while there's a problem where we need to construct a code with some properties, with good rate and good distance, and further properties. And you try these two, and if they don't work, you're out of luck. So we desperately need new approaches to this problem. Okay, but so these are really, really nice codes. These were discovered by Sipser and Spielman. Quite recently, so this is 95, given that everything else I said last class was ended in the 70s, right? So this is recent, and but there were hints of ideas related to this by Tanner and Gallagher long before. Okay, good. So these are codes which are going to be based on expander graphs. And so they come from and all the reasoning about them will be totally combinatorial. There's not going to be any algebra. So I need to say what expander graphs are. So expander graphs. Okay, so I will look at a specific kind of expander graph. These are going to be bipartite graphs. There are going to be n vertices on the left, m vertices on the right, and in my setting m will be less than n. All the vertices on the left are going to be C regular. All the vertices on the right are going to be D regular. So in particular, n times C, right, equals m times D. Right? So there's a relationship between them. And so n and m, and there's also C and a D, and we know that n times C equals m times D, and since m is less than n, C is, since n is more than m, C is less than D. Okay, good. So this is our setup, and so we say this graph is delta gamma expanded if for all subsets of the left hand side, so this is, I'm calling the left, this is the right, the set of neighbors that it has is big. Okay, so for all subsets of the left hand side with size at most delta n, the set of its neighbors, which is, so I'm going to write that like this. This, by the way, is the set of all vertices V on the right hand side, such that V has a neighbor in S. Right, so this set, the size of this is at least, so I took a set here. What's the largest the set could be?
Size of S times C.
Size of S times C. So if it's 1 minus gamma times that, so it's 1 minus gamma times size S times C times A. This is called delta gamma expander. Sets which are not too big, there's a delta sitting there. Sets which are not too big have many neighbors on the right. If this was 1, it would ask that all the neighbors are disjoint. That's important. That you can't have in this setup. but it's almost 1. And this you can have. And why can you have it? Well, it's a pseudo-random property. If you pick the graph at random, random amongst all graphs which are CD regular, C on this side, D on that side, then for a small enough delta, you will get almost full expansion. So this is a fact from which can be proved by the probabilistic method. It is not easy. It's not the first exercise in the probabilistic method. Already the fact that you have to choose this graph carefully is an issue. It cannot be picked by just taking C neighbors for every vertex independently at random. This will not do the job. You will then end up with isolated vertices on the right. So if you really want this, you'll end up with bad configurations. You need the CD regularity, and you have to choose it uniformly among such things. So even how do you analyze that? Anyway, it's a good exercise to try to show that such things exist. These things do exist, and they exist in quite good generality. So this clearly cannot exist for sets where delta is as big as 1/100th. No, if this thing ends up being bigger than m, it's not going to happen. So for some fraction, delta being, let's say, gamma factor less than m, delta being so small that this is at most a gamma fraction less than m, this does exist. So the fact that I need is that such graphs exist with delta being omega 1, gamma equals any small constant, and then n and C and D being constants. C and D constants. Right, this omega 1 will depend on the C and D, and n and m going to infinity. In this asymptotic setting, these graphs exist. So this is the fact that we will use. At the time Spitzer and Spielman came up with these codes, we did not have explicit examples of these codes. But since then, we have found explicit examples. So more recently, such graphs can be found explicitly. There's a beautiful result of CR, VW, Kapalbo, Reingold, Vadhan, Wigderson, based on the zigzag product, I guess, 03, and two very, very recent papers. I really, really like these, by Kolovich and by Dashma and others. I forget which, based on high-dimensional expanders. But yeah, these are really clean and elegant. I highly recommend looking at them if you're interested in these kinds of things. So such graphs can also be explicitly constructed.
Yeah, I'm not sure, but I think Capalbo Reingold is just when the ratio between n and m is like almost quadratic.
Yes, but
I think there is a boundary like on the ratio between n and m.
Right, so it doesn't do in every asymptotic, but it does do it in the setting of constant imbalance, which is what is needed for us. Yeah. But CRVW does not construct all expanders which are not exist. Yes, that's right. Okay. Good. Okay. So now, so this is so let's acknowledge that this is some heavy pseudo-random input that's coming into our code construction. So after we construct the code, we have to wonder, how much of the work was done by this, and how much of the work did we do after this? But yeah, so there'll be some interesting stuff coming, but there is a lot of making this has a lot of ideas already inside. Okay. Good. So here is the definition of the code. It's a very, very clean definition. So here's the code. So it defines C as follows. So this graph, we are now going to view these as the code word symbols, So we're going to write zeros and ones on the vertices. And we're going to view the right-hand vertices as parity checks. They're going to enforce constraints on their neighbors, and the constraint they're going to impose is the sum of all those bits mod 2 should be 0. Okay, so the code C is all functions, so it's going to be, I guess, functions from the left-hand side to F2 such that for all vertices on the right, the parity of the neighbors, so the parity over all u in L, u neighbor of V of f of u is 0. That's the definition of the code. How many constraints have we imposed?
M.
M. So the dimension of C is at least n minus m, because we imposed m constraints. They may or may not be linearly independent, so we leave the dimensions. So it has some, and if n and m are, if C and D are constants, then n and m are some positive ratio of each other. So this is going to be omega n, the way I set it up. Okay, and C has distance, and I guess this is lemma. C has distance, omega. Okay, and the proof of this is very, very clean. We need to show that if there's if you cannot have a code word, namely an assignment of zeros and ones to the left hand side, which satisfies all the parity checks and also has very few ones. So suppose we have a set S, and we had only ones on this and zeros everywhere else. Then we want to show that it cannot be the case that all the parity checks are satisfied. So take any code word X, let S, we're going to show that it's if it's we're taking a non-zero, and we're going to show that it cannot have too small a support. So let S be the subset of left hand side with size be the support of X. Okay, so we want to show, so if size S is at most delta, it's going to be the same delta. We want to show, we claim that some parity check is unsatisfied.
It should be delta times mod L, right?
Delta times?
Mod L, right? Delta is between.
Correct, delta times L, that's it. Some parity check is unsatisfied. And okay, and this will also depend now on this gamma. I said if we think of gamma as something small, the gamma will have to be at most half for this to happen. So maybe I should actually add that. If gamma is at most half. Okay. So we have all these parity checks. When is a parity check unsatisfied? Where it has a bunch of neighbors. Let's say these were the three neighbors. Is this parity check satisfied? Yes, because 1 plus 1, there were two errors in its neighbor. I'm calling them errors. Yeah, there were two ones in its neighborhood, and they cancelled each other out. If it has an odd number of ones in its neighborhood, we caught it. Okay, so we want to show there is a constraint with an odd number of neighbors in S. So this is a constraint is an element to the right. Okay, so odd is a very hard thing to reason about in this kind of expanded thing. So in fact, we will show something even better, which is so we'll show that there's a constraint with one neighbor in S, exactly one. Okay, so why is there a constraint with exactly one neighbor in S? And this will come from the super expansion of the set S. We have so our set S, the neighbors of S, it's a big neighborhood. The neighborhood is so big that it could not be that every vertex here has two neighbors in S. So that math just doesn't work, and that's why this expansion factor half happens. So isn't it there? So since the neighborhood of S, S is at most delta n. Conveniently, it's the same delta n of my expansion. So the distance delta is going to be this delta. So we get that. So by the expansion, let's respect that line. Okay, so by the expansion, the size of the neighborhood of S is at least 1 minus gamma times delta times the size of S times C, which is at least half C times size S. So you, I want maybe strictly greater, right? So this gamma is strictly greater than half. Did I say that? No, I didn't. So cannot have two neighbors per right vertex. I mean, so I'm just redrawing the action here. There are so this was S, whatever it was, and this is one. This is greater than half of C times S, and there are CS vertices coming out total. Right? CS edges. There are C size S edges coming. If each receives 2, they're just too many to receive. So that so that doesn't. Okay, good. So we now have that it has distance. We got distance from some very harmless property. It's just that the expansion is so much that there are unique neighbors. Yeah.
Is it known that if we have gamma equal to 0.4999?
Yeah.
Or I guess like slightly worse than the value required here to get unique expansion, do we still get an expander code, or are there examples where it breaks?
That's a good question. I do not know if there are examples that violate it.
Isn't sufficient to be locally peelable, like to have a matching kind of structure? Like I think peelable should be enough for this property to.
So what does peelable mean?
It's just like instead of having like always a unique neighbor, you're sure that there exists a matching from each subset that you can define on the left-hand side.
Maybe. Yeah, so I don't know. I don't know any variations of this constraint that actually guarantees expansion. So I don't know of any. There may be out there, but I do not know. We are fortunately only fighting against true code words, those that satisfy every single constraint. So it's we do have a lot to work with. We didn't use so much in this. Okay, other questions? Right, so so using this very strong pseudorandom object, which already has this constant sets of constant fraction size expand extremely, they have extreme expansion, then we do get a code with good distance. And it's a code of a completely different shape from the one we saw before. It's it ultimately depends on how the expander is made, but given how expanders are known to be made, especially let's say that, so this is a really nice code. At the time of Simpson experiment, even though the codes were not explicit, because the graphs are not explicit, these codes already had a lot of impact. So these codes have a really nice decoding algorithm. So the decoding algorithm can be made to run in linear time on the appropriate machine model, or more explicitly, there are linear size circuits that can do decoding. So we will see this decoding algorithm now. Okay, so I want to make note of a fact that comes out of this extreme expansion. So which is that for any set S inside the left hand side, the set of unique neighbors, the size of U of S. What is unique neighbors? So this is the set of all X in the right hand side of V in the right hand side, such that there exists exactly one U in S, such that U is in a neighbor of V. Those vertices on the right that have exactly one neighbor. This is also B. This is at least some function of gamma. And so let me see what that function is. That it is 2 gamma minus 1 times the size of S times C times the size of S. And where is that 2?
Gamma is less than half, right?
Yes.
It's 1 minus.
Yes. So it's 2 times my other, my gamma was actually 1 minus gamma. So what is this? 1 minus 2 gamma? Yes. Okay. And let's see why, so that it will keep me honest. So here was our set S. Here is the neighborhood of S. And let's say this is the unique neighbors of S. And this is the non-unique neighbors of S. Right, then we have all these edges going out. The size of the neighborhood of S is at least 1 minus gamma C times size S. And this is the size of U plus the size of N. On the other hand, only one edge comes to all of these. And this gets at least 2 edges. So since this gets at least 2 edges, 2 times n of S. So the total number of edges coming out, which is C times size S, is at least 2 size of n plus size of U. And so now I'm going to manipulate times 2 minus this. And the inequality goes the right way. And I get so 2 times this minus this, which is size U is at least 2 minus 2 gamma minus 1, which is 1 minus 2 gamma. Yeah, good. Okay. Good. So sets, so if gamma is really small, not just half, but say 0.1 or 0.01, then every set has many unique neighbors too. Okay, this is and this makes sense. I mean, you're expanding by almost the degree factor, so everything basically has to be. Okay. So now we'll see the decoding algorithm. Yeah. So the decoding algorithm has a 2-word description, but you cannot do it unless you've seen these 2 words before. So it's called belief propagation, somewhere out in machine learning and statistical physics. Okay, so the thing to note, or the viewpoint that makes this, that inspires the decoding algorithm. So we have all these constraints. We have all these vertices. All these constraints are trying to get happy. Okay? We were given a corrupted code word. So we took a true C. If you had a true C, then all the constraints here. So these are the constraints. When this was the true C, all the constraints were happy. their constraints were satisfied. Now we're going to perturb C a little bit. Remember, the decoding problem is you're given something which is a perturbed code word. So it's promised to be close to a code word. So let's think of the original code word, and then a few of the bits have been changed, have been flipped. These are going to now make some constraints unhappy. So all these constraints are, so we have a whole bunch of happy and unhappy constraints. They all have opinions about the current state of the world. So our goal is to try to make as many constraints happy as possible. So we have happy and unhappy constraints. We try to make as many constraints happy. Good. So let's just, as a thought experiment, consider just one bit was corrupted. How are the constraints going to look? How many of them are happy, and which ones are happy and which ones are not? So we have all these constraints. Initially they were all happy. After you flip one bit, all of its neighbors are going to be unhappy. Okay. So by looking at the vertices on the left and seeing how many unhappy neighbors does this vertex have? Well, it has a few edges. In this particular case, it has one unhappy constraint. This one has one unhappy constraint. This one, all unhappy constraints. It's standing out by how many unhappy constraint neighbors it has. This helped us identify the error that happened. So the constraints are, we are trying to fix the bits on the left in order to make all the constraints happy. We're going to sort of blindly go to vertices which have the most number of unhappy neighbors, and if not just most, there should be more unhappy neighbors than happy neighbors. And then if we flip the bit, it will flip all those unhappy ones to happy and the happy ones to unhappy, and then we will have reduced the number of unhappy constraints. So this is going to be a strategy. So try to make as many. So we want to make steps which improve the number of happy constraints. So we look for a vertex which has more unhappy neighbors than happy neighbors and flip that. This is the algorithm. So this is the whole algorithm. Look for a vertex V and L that has more unhappy neighbors than happy neighbors. Flip the bit on that, the bit written on that, written on it. And this is the algorithm. So the fact that it works, I need to prove a bunch of things, that you can find such a vertex, and at the end we will, I need to prove some things, but this is the algorithm. It's extremely simple. Questions about the algorithm? And this is some kind of, it's a nice way of satisfying a bunch of constraints, to look for small modifications that try to improve the number of constraints that are satisfied. And in this particular case, it has the nice property that if you start with a true solution, and perturb it a little bit, then starting the algorithm at such a spot will bring you back to the true solution. This does not happen for any old CSP with any old constraint, but for this particular one it does. Okay, so let's see why this works. So first observe if we make a step, we have improved the number of happy constraints. Each step improves the number of happy constraints. Okay, this is just that's the definition of the algorithm. Okay, now I need to show that there is always a vertex for which there are more unhappy neighbors than happy neighbors. So here is the claim. If we start with a received word, so this is a received word that has few errors, then there is a constraint. There is a vertex V on the left, a U on the left, that has more unhappy neighbors than happy neighbors. Okay, why is that? This is our M, this is our N. We start off with a small set of perturbed. This is a small set of corruptions. Why is there a vertex which has more unhappy neighbors than happy neighbors? So the only set of constraints that have the potential for being unsatisfied are contained within the neighborhood of S. All unhappy constraints are within this. But maybe nobody is unhappy. If there's a unique, yes, good. Maybe there's only one unhappy. This is an impediment to the algorithm. If there was only one unhappy constraint, then we're in trouble. So how come? Yeah, how come this doesn't arise?
So there are many unique neighbors.
There are many unique neighbors, right? So underlying this fact, yeah, there are many unique neighbors, and here we'll have to use gamma being not just smaller than half. We'll have to make it much smaller than that, maybe smaller than 1/4 or something. But there are going to be many unique neighbors. Right.
So there must be a vertex on the left-hand side
Mhm.
which has many unique neighbors,
Right.
and it has many unhappy constraints.
Right. All unique neighbors are unhappy. So if you can find many unique neighbors, you have found many unhappy constraints. The way this expression is, the number of unique neighbors 1 minus 2 gamma times C times size S. This is the total number of neighbors at most C times size S. So we are, yeah. So this is if gamma is really small, this is going to be a big fraction of all neighbors. Okay, so many unique neighbors. So if S is small, S has many unique neighbors. So for S being the set of corruptions, being the set of corrupted coordinates, which we know is less than delta size s, delta n. I need to discuss this soon. So there are a set of corrupted coordinates. We know it's less than delta n. The size of size us greater than 1 minus 2 gamma times size s times c size s, which is greater than half of c size s, which is at least half the neighborhood of s. At least half the neighbors, at least half the neighborhood is unique neighborhood, and all elements of US are unhappy constraints. So there is a vertex V and S which has at least half strictly equilibrium. Its neighbors unhappy. I wanted to fix something. Oh yeah, so for this assumption, for this step, I needed gamma to be less than 1/4. Okay, so this needed not just half expansion, which we already didn't know how to construct. It needed 1/4, 3/4 expansion, or the gamma being 1. Okay, so this is why we can make progress. There's something missing.
You can flip like something outside.
Pardon?
You can flip something outside of S and increase the distance from the.
That's right. As we kept, so first of all, we're not promising that every step we make takes us closer to the satisfying assignment. What we're doing is we're improving the number of satisfied constraints. That's different from changing the word we are at in the direction of the true satisfying assignment. Okay, so what this could mean is that in the process of making more and more constraints satisfied, the word that we're maintaining on the left has gone further and further away from the true code word. At that point, S might be too big. If S is too big to apply this expansion assumption, then we do not get this argument. So we need to also show that at every step of the algorithm, we do not go too far from the true code word. So need to make sure that at every step of the algorithm the distance of the current word from the original code word is at most delta. Okay, why is this? So this is a bit strange. We have made an algorithm. It is improving something. It is improving the number of constraints, but in the process, it is going possibly farther away from our true code word. And this can actually happen. It's not true that it's also the case that our word always goes directly towards the correct code word.
Should
Yeah.
we try to ensure the distance is at least delta n by 2, because at distance delta n there can be 2 code words at that.
Yes, so I slightly fudged something, which is so actually, yeah. We started off with a code word which we know is close, right? So we're going to maintain that property. Okay, yes. So this is going to be actually a little bit smaller. Yes. So let's start at half. That's good. Yeah. So I cheated somewhere. We started with some received word. I needed to say how close it was to the code word. Here I only used that it was less than delta n close, but later I will use closer. Yes, that's right. Okay, so we are close. Also, I should say the distance of this code is more than delta n. It's actually maybe 2 times 1 minus gamma times delta n. So it's slightly more than delta n. I just didn't prove it. Yeah.
Can you explain again why the last line on this?
So this is S. This is the neighborhood of S. And we showed just now that the unique neighborhood is more than half. Now every vertex has some of its neighbors in unique and some of its neighbors outside. So this is by averaging. The unique neighborhood is a large fraction of all neighbors. So for each vertex, there is the fraction of neighbors which are in the unique set, and the fraction which is outside. And yeah, and is that? No, I didn't say any, I didn't say enough. Okay, let me say it slowly. So the size of the unique neighborhood of S is the sum over all vertices in S. Let's call it U sub V. Or let's say unique. So n sub V. It is the number of unique neighbors of that V. And the neighborhood of S is okay, this is something else. I want this to be more than half. And what am I saying?
Would it just work if you pick a random vertex in S and
right.
Look at the expected number of U vertices in U versus vertices
right.
outside of U? So
right.
I know that U of S is greater than N of S.
Right.
So I mean, in expectation, being a bit handy, good.
Right.
And linearity will tell you that it has to be greater, so there must exist some vertex where it is greater.
Right. Each vertex here contributes some number of unique neighbors. The unique neighbors only come, they're assigned to a vertex on the left. Right? Unique neighbor is unique to that. So each vertex is contributing its own. So one of these is contributing, take the one that's contributing the most. That's going to be more than half. Why is that? That's.
But what if they are all connected to the non-unique?
Oh no, but the
S?
fact that they are in unique S means that they came from some vertex. They are neighbors.
Wait, is it unique for the vertex in S, or is it unique for the?
No, it's unique for the vertices in S.
Oh, okay.
So unique in S means that they come like this, right? So each vertex here has some set of neighbors which came in unique S, and the rest go into NS. And this other vertex also has its own private unique collection. Okay, so all the sizes of all these sets added up to more than half of CS. So one of these has size at least half C. Yes, good. Okay, so okay, so maybe I could even stop it there. Yes, let me stop it there, and then I'm very happy. Then it's maybe even better, right? The size of the unique neighborhood is more than half CS. Therefore, some element there has more than half C unique neighbors, and half C is more than half of C. Yes. Okay. Good. So at least I got convinced. No. Okay. We'll talk again. It's okay. Okay, so we want to make sure that at every stage we do not end up going too far. Okay. And now the reason for this is if we ended up going too far, on the way we were moderately far. If you're moderately far, then the set of corrupted vertices, let's say S, is it must cause many unhappy constraints. Why? Because this was our unique, because of unique expansion. If you have many unhappy constraints, you have more unhappy constraints than what you started, and so this cannot. Okay, because we have made sure that at least the number of constraints, unhappy constraints, is always reduced. Okay, so if we ever go very far, at some point we must be moderately far. Consider that point. Okay, so let S be the corrupted set at that point. S be the corrupted set at that point. Then the size of the unique neighborhood of S. So number of unhappy constraints. This is at least the size of the unique neighborhood of S, which where am I using that it's moderately far and not very far? It's I want to be within the zone where I can apply unique expansion. So then the size of the unique neighborhood of S is at least size S times C times 1 minus 2 gamma. Okay, so let S be the thing, and with size S being at least, let's say, delta n. Then what we end up with here is at least one, let's say, do I need to say delta n? Okay, I'm saying delta n, but so that I can apply the expansion rule. So this I get 1 minus 2 gamma times delta C times delta n. But I know that the number of unhappy constraints has only strictly reduced from where I started. Okay, so now I can say, I didn't give you a proper theorem statement. My proper theorem statement would have been, suppose you start with a received word which is this distance from a true code word, then at the end you end up with a true code word. That this distance I'm going to set in order to make sure that the number of unhappy constraints is less than this, so that we will never violate this. Which is more than the number of initial unhappy constraints. Okay, now I have to tell you what's the initial number of unhappy constraints. So yeah, so this algorithm works. So this was the claim that maybe I should have said. And the claim is this algorithm decodes from 1 minus 2 gamma times delta n. Yeah.
Why is this in your time?
Good one. So
because number of happy constants is increasing at each step.
Oh, this is the number of iterations. You're worried about implementation details, or you're worried about number of steps? Implementation details? Okay, so I'm not the best person to answer this. It depends on your machine model. On a one-tape Turing machine, it's not. On a multi-tape Turing machine, I believe so. RAM model, I don't know. It's something to do with data structures and implementation. I never, I can never tell the difference between machine models. It gives a linear size circuit. I can convince you, I think, and I think it's almost obvious. But linear, I don't even exactly know the proper definition of linear time. So sorry, and I'm too old to learn it. Yeah, but it can be done.
But so when you flick a vertex, only constantly many constants get flipped. So you
Right.
can maintain them in some data structure. And
Right, you have to maintain some data structure, and you keep a list of all the number of violated constraints for each.
but since the degree is constant, this would be easy.
Right, the degree is constant. Right, so every time you update this, all these constraints get satisfied, and then you go to all their neighbors, and the status of the number of violated constraints for them gets changed by 1. Okay, so that's the answer maybe, right? So good, yeah, thanks. Right, so you only have to update a constant number of vertices every time you do this. But your machine model should allow you to hop to any vertex you want, to make sure. Yeah. Good, so you should, yeah, so this required gamma less than 1/4. So this is less than half the minimum distance that I proved. But in fact, the distance of this code is slightly larger than what I proved. It is more than delta, and it's maybe delta plus 1, 2 minus gamma times delta times, or 2 minus 2 gamma times delta times. So it is actually bigger than what I proved. Okay, question. So this was our totally different example of a good rate, good distance code, building upon this expander graph, and yeah, and it comes with a beautiful decoding algorithm of its own.
So the decoding algorithm works like in less cases than the distance of what we required something more for the algorithm work?
No, oh right, it's not half the minimum distance, but it is some fraction of the minimum distance.
Oh, it's it.
Yeah, so it is still a constant fraction of errors that it can correct. It's so when we say half the minimum distance, we don't really know the minimum distance of the code. I just happen to prove a bound for the minimum distance of the code. So it's there may be a better bound, a better lower bound.
No, but we required more from the expander than before?
Oh yes, that's right. We did require that the expansion is more than 1/4 for this algorithm to do decoding. It is known, there's a result of Witherman that shows how to do it for when the expansion is, when this gamma is 1/3. No, not 1/3 is the correct direction. Yes, when gamma is 1/3, it's known how to do it.
Whose paper is?
Witherman, Michael Witherman, Widerman. You had a question?
Oh no, I got it.
Yeah, okay, great. Yes.
On the right side, which is more than 1 minus 2 gamma times c times delta.
Right.
The claim is the decodes from 1 minus 2 gamma times delta without c.
Oh yes, this is the number of errors,
Okay.
and therefore the number of unhappy constraints at the beginning
Oh.
is at most c times that, and that I set it up so that it's that.
Oh.
If this is the number of errors, the number of unhappy constraints is at most that. And right, so yeah. And the number of unhappy constraints only keeps strictly reducing at each stage. So by the end, you have 0 unhappy constraints. You always are able to proceed because yeah. Yeah.
Do you want to say anything about encoding?
Yes, good question. These codes we only know how to encode in I guess quadratic time because they have been defined by linear constraints. Yeah, it's been defined by constraints. It's not yeah. Okay, and there are other codes. These are the Sipser codes which came 1 year later, which also have linear time encoding and linear time decoding. They're based on some recursive applications. Yes.
Just for reference, there was like a paper in like 2010 who like claimed that all LDPC codes could be
right.
encodable in linear time,
right.
but it's not true. So
right.
if you see a paper if you see this result, just know that.
Okay. Yeah. Oh, good question. Good comment. Yes. Yes. So there was a claim by credible people that any code which defined by such a thing can be encoded in linear time, but it's not true. Okay. So this expander code is an instance of a slightly more general family of expander codes. These are called Tanner codes. where the constraint which we applied on the right is of a particular form. We ask that the neighbors of every vertex form an even weight word. This is the constraint of parallel. The set of all even weight strings is a code of distance 2. One could consider replacing that constraint by asking that the neighborhood of every vertex is in a certain code, which I chose, a certain code of length d, which I chose, which has some property. This is an interesting family of code. So I will make the definition of the code, yeah. So did I already? No, I didn't. So this is a variant of the Sipser-Spielman construction. It was also done in Sipser and Spielman, and they also gave a linear time algorithm for decoding these codes. Good. So we have M, we have the N, and now we have vertices like this. Okay. This is D regular. This is C regular, and then the new code in this. So we start with C small, which is some subset of F2 to the D, okay, with minimum distance D0, for example. Then define C to be the set of all functions from the left hand side. This is L, this is R, to F2, such that the constraint imposed is that of membership in C small, such that for all V in the right, the set of F of U, U adjacent to V, this is a tuple, is in C small. And we have, so we have thus imposed constraints. Okay, so now I can, so this is a code, and it turns out to have, turns out also to have good distance. And the new distance depends only on D0. And okay, so maybe I can even give a quick, yes. So let's see the distances. It's not a bad thing to see. So
here are you requiring expansion property?
We still require an expansion property, but we require a weaker expansion property than the expansion property that we required before. So previously we needed expansion at least half before anything starts happening. Here we can get away with expansion less than half. And at the time of Sipser-Spielman's paper, we did no explicit expanders with expansion less than half, so that their construction could be instantiated in to give an explicit construction. Yeah.
Can you get anything if instead of like asking for a set of size delta n to expand, they just guarantee to you like I don't know poly n sets that expand?
There are poly n different sets that do.
No. If instead of asking that every set size less than delta n,
yeah.
I ask you every set of size less than delta poly n. Do you get anything?
Oh, something like square root n, you mean?
Yeah, let's say square root n.
I see. No. That kind of property we do have we have easier constructions of such things, and from those we don't know how to get constant rate codes. Constant distance codes. For constant distance, you really need expansion for sets all the way up to linear sets, at least as far as we know. Good. So then C has good distance. Good distance. So let me say why. So we're assuming again that this is a delta gamma expander. Then, okay, so the proof is basically the same. We choose a subset, choose any subset S in the left hand side. So the claim is so right. So then the claim is, so this set is going to be the set of ones, right? We're going to have zeros everywhere else, and we're going to have a set of ones, and we're just saying what's the smallest weight you can have while still being able to satisfy all the constraints that are there. So so what this means for us is that since the neighborhood of every right vertex is supposed to be a code word of this code of minimum distance delta 0, I should have said this is a linear code. So since it's supposed to be a code word of this code of minimum distance delta d0, then if a code word has any neighbors in this set, it should have at least d0 neighbors in this set. So choose any subset S. We want to show that some vertex in the neighborhood of S. So this guarantees that there is at least one neighbor has at most d0, strictly less than d0 neighbors in S. Okay, and why is that going to happen? This will happen if so we have so the neighborhood. We want a vertex which has less than d0 neighbors in S. So what's the total number of edges coming into this? There are C times size S edges coming into neighborhood of S. So each right vertex, each vertex in gamma S is receiving the average number of received edges is C size S over gamma S. So if this is less than d0, I think then we are happy. Then there exists some vertex we desire. What was this word desired? This vertex. That's the vertex we desire. So that's our condition. C size S. C size S over gamma S less than d0, which is the same as the size of the neighborhood of S should be at least C over d0 times size S. And this is our expansion now that we require. The distance, instead of C times 1 minus gamma times size S, it becomes C over d0 times size S. So if d0, the distance is 7, we are only asking for a factor 1/7 expansion, which is much less than what we had before. Okay, so this is right. So when d0 is 2, which is what happened in the case of the parity check constraint on the right, we got at least C over 2. I guess we need this. Yeah, we need expansion slightly more than C over d0. So we can get away. So can use weaker expanders to get explicit good rate, good distance. Good stands for omega 1. So omega 1 rate and delta. Okay, and so this is truly an explicit construction now, where the kind of expanders that you need in order to implement it are much more reasonable. There are many constructions of codes of expanders that have this property, which is Yeah, so it's not as fancy as the previous one. Okay, so this is now slightly more tangible as an explicit construction. Okay, questions about this?
Does this also have a decoding?
This also has a decoding algorithm, linear time, and it's based on a very similar principle about happy constructs. Yeah.
What was the quadratic encoding thing?
The quadratic encoding is this is a linear space. So it has a matrix defining the space. You can find a basis for it in I see. N to the omega time. I don't know. So yeah, okay, fine. N to the omega time. So let's step back. Usually the code is fixed. So if you have pre-processing time with the code, you find the generator matrix once and for all. We're not going to search for it each time we encode a code word. So you find the generator matrix once and for all. It is some n by omega n matrix, which is it's a matrix containing all the basis vectors of this code, and then multiplying by that, then it's good. Yeah.
So not just a straightforward linear algebra thing to take the parity like the check matrix and convert it into the generator matrix?
So that is that requires n to the omega time.
Oh, I see.
Yeah, so I wanted to pre-process so that I get the generator matrix once. I don't want to get the generator matrix each time I get a code word. Yeah. Okay, other questions?
So in the first construction, we didn't need like the regularity on the right hand side, right? Or
Did we use regularity on the right hand side? We did not need. Did we use it? In this thing? No, I think I was okay, right? I thought the final proof of this was really smooth. Right?
You need to know that there's at most 7 times size of S neighbors, no?
Yeah, that's the regularity on this side. Regularity on this side we used. On that side we didn't use it. I think we didn't use it. Yes, that's right. And in fact, the CRVW construction does not produce regularity on the right. Yeah, so yeah, we don't need it.
So for this construction, you also have to actually specify an ordering on L, right? Because you're saying the neighbors of.
That's correct. That's correct. Every neighborhood, unlike the parity check, which is a symmetric constraint, every neighborhood of this is D vectors, and we have to pick an ordering for it.
And so we do that once for L, or do it separately?
It does not matter for this proof. For each vertex, you could choose your own local ordering as you wish. And so in particular, there's some flexibility here, which is maybe choosing better orderings gives you better distance. And probably it does. In fact, if you probably pick it at random, it's probably as good as the GV bound or something. There's so much flexibility here, and usually with a little bit of flexibility, you can get a lot.
And the decoder also works for any ordering? Or?
The decoder works for any ordering. That's it. The only property being used is the distance of this of the views that these right vertices get. Okay. Other questions? Okay, so this was another totally different good rate, good distance code. I will now move to a new notion of decoding called local decoding, which will give you decoding in time even faster than linear. Okay, but it comes at a cost, and we have to change the definition of what decoding means. And that's just because if your answer is linear size, which is this, if the problem of decoding is find the true code word, then the answer is linear size, then you cannot hope to run in sublinear time. So we'll have to change the definition of decoding to local decoding, and then we will have a nice construction. Okay. So local decoding. So we're starting. This is a new start. So if you got lost before, you can join and get lost again. Okay. So we want to decode in time lit low of n. And can you even do this? Okay, so to motivate this, I will give you the whole story of how error correcting codes are used. Right? So you have your message, when it goes And at the end, you have you receive. So this fellow wants the message. And this is the original story of error correcting codes, where people are sending things on chance. So you have the message. I want to send that message to that person, but along the way bits are going to get flipped. So if you sent the message originally, there will be trouble. So instead you encode, and then you get a code word. Right. Oh, so actually I should draw it. Code word. Right. We expanded it. Then then it got corrupted, and then it gets received by the decoder, which will then decode it and find the message. Right? And just for sanity, this is in sigma to the k. This is sigma to the k, and this was sigma to the n. Right? And it started off as a code word, and then it got messed up. Okay. So, but now another variant of this problem is, so the story is less like communication on a channel, but it's more like storing on a hard disk. You have your data, you put it on your hard disk, then time is the channel that rots it, and then later on you want to go back and you have taken 1 zillion photos, but you actually just are going to look at one of them. And that's what you care about. Can I have access to that one thing that I wanted to look at? So we're changing the story. So there's the original message. It gets stored, encoded into a big code word. And then at the time of decoding, you don't want the whole message. You just want the ith message symbol. Okay, so you get this decoding algorithm that has access to this. It also gets I, and it outputs ith message. So maybe it makes sense to consider this variant of the problem, where you just ask for the ith message symbol. And now we do not have this barrier that the answer size is linear, so you need to run in linear time. There's a hope to run in less than linear time. Okay, so, and as with all sublinear time algorithms, if you wanted to have a reasonable hope of doing it, you would need to use randomness. Just because if it was a deterministic algorithm that is going to run sublinear time, it is only going to be able to inspect a sublinear number of bits. And if it's deterministic, it's a fixed sublinear number of bits, and if the corruptions happen there, you have no hope. Okay, so I now give you the definition of local decoding. So local decoding, I guess a locally decodable code. Okay, so it comes with an encoding map and a decoding map. Okay, so it's a subset C in sigma to the n, a map E from sigma to the k to C. This is a bijection, and a map D from and the decoding map is actually Sn, and decoding map that takes sigma to the n, but it's actually oracle access. So let me actually write it, and a decoder D that gets I and k as input, and oracle access to some received word R in sigma to the n, such that if the distance of R from the encoding of x is less than some delta prime, then with high probability the decoder on input I outputs the ith bit. Then probability that d of I with access to R equals xi is at least 0.9. And what's this probability over?
Internal contour.
The internal randomness of the decoding algorithm. There's no randomness on I. Did I say for all I? I didn't say for all. I need to say for all. For all I, and this is a for all R such that this happens, and this is over the internal randomness of D. Let me propose an algorithm first for decoding any code, and then you tell me what's wrong. The decoder is when given. Oh, I see. Oh, sorry, I messed something up. We are getting bits of the original code. So this is locally decodable. There's another word called correctable. Let me also define correctable. It's almost the same. Correctable. Oh, it's a different color. Yes. So the red is the correctable stream. Blah, blah, blah. You don't need the encoding map for this, so that's why correctable is slightly cleaner. You don't need the context of the encoder. So the decoder D so that it gets I and N, an input to some received word, and if the distance of that received word from some code word Y is less than delta prime, then the probability that it gives you Yi is at least 0.9. Did you understand the difference? In a locally decodable code, you are getting the ith bit of the original message. In a locally correctable code, you are getting the ith bit of the true code word. Often these are interchangeable because in many error correcting codes, the message is part of the code word, or you can arrange for it to be so that the message stays as is, and the code word is just adding on a few extra symbols to the existing message. So these are often very similar. But I like correctable because you don't have to talk about the encoding message. The encoding map. Okay, so now here's an algorithm. The decoder is given I and given access to some corrupted code word R. It knows that R is close to the code word, so most symbols are right. So on input I, it outputs Ri. Is this a locally decodable? Is this a local decoder or local corrector?
It's only outputting most.
Yeah, it's only getting the answer right for most I. But here the emphasis is on for all I. Yes?
No, because there is a code word, like it'll be right with probability 0, which is not more than 0.99.
Why would it be right with probability 0 if it's...
Say the code word which is wrong in the first bit.
Yeah.
Ask for the first bit.
Oh yes, good. Yeah, then it will be the probability of correctness is 0, right? Correct. There are some i's for which it will be 0, and there are some i's for which it will be 1. But we want at least 0.99 for all i's. So this is a way of dividing out the errors amongst all coordinates. Yeah, so it changed. So from for most, so the average correctness is still right, the same basically, but we have made sure that there is a lot of correctness in every coordinate. So that's a definition. It's very easy to make definitions. This definition actually came 10 years after the first locally decodable code, when people started to formalize what is this miracle that we just saw. So this miracle that we just saw was a whole bunch of error correcting code technology and property testing technology that was discovered during the proof of the PCP theorem and interactive proofs, and there were all kinds of miracles that happened in, let's say, between 1987 and 1993. Allegedly, I wasn't there. And then after all the, after the whole world was turned upside down by them, people sat down and started analyzing the ruins. And so this is one of the definitions that came after that. There's another nice definition called locally testable code, Okay, I will define that too. Okay, so locally testable code. You will hear us talk about some amazing locally testable code solving some old open problem by lead GA tomorrow. A locally testable code, okay, so it's a code in sigma to the n. We don't have an encoding map, and it has a tester T that's going to tell you, that's going to detect whether a given string is close to the code or not. T, that a given oracle access to R in sigma to the n has this behavior. If R is in C, then the probability that the tester with oracle access to R outputs is going to output accept or reject. Equal to accept is 1. It always accepts true code words.
Sorry, could you use another pen?
Oh yeah. Do I have to rewrite this?
No.
Okay, good. So it's 1, and no. Yes, and if R is not, so if R is far from the code, if so let me first start with this, and then we'll see probability that TR is accept it is less than 0.5. It's a tester that does this, and yeah, okay. And now we can hope to do this in sublinear time, maybe. True code words are accepted. So we're trying to do this in sublinear time. True code words are accepted. Non-true code words are rejected. Is this something we can hope to do in, let's say, polylog n time? Yeah, no, why not?
So if only one bit is corrupted and you check polylog n bits with very low probability, it will detect.
Right. So if this is too delicate a property to hope to catch it, right? So just like in property testing, you only can do it when R is sufficiently far from any code word. So it has to be noticeable. So if the distance between R and C is greater than 0.01, this is the relative Hamming distance, then the probability of acceptance is less than 1. And once you do this, then it's potentially 100 queries will witness this with pretty good probability. So you can hope to do it with a constant number of queries into the received word or at polylogarithmic time. And yes, and so we care about, and even in this case we care about number of queries into R, and also the running time to a lesser extent. Yeah. And so good questions are, can number of queries be constant? Can the running time be polylog n? Running time cannot be less than log n, just because the tester and decoder has to be able to talk about the ith coordinate, and that's already log n. So the log n is anyway threshold there, but potentially you could have constant number of queries for these things. And okay, so let me actually tell you the status of this. So for LDCs and for LDCs and others, okay, and LCCs are slightly different also. So let me and LTCs. Okay, so the famous result that Lee J will talk about is that this can be done with good rate and good distance. This is really amazing. For this, no Oh, and by the way, in all of these, distance had to be constant. Otherwise, it doesn't make sense. I mean, this delta prime is going to be a constant. So in all of these, delta is omega 1 for all. LTCs and LDCs. At least for what I'm saying right now. So no, you cannot have this. The rate, you just cannot have it. Yeah. You need it. Number of queries has to be at least log n. And so this also, I guess, well, this we don't know. And this is, yes, by the same construction. Okay. So, but we do know some very interesting locally decodable codes, and I will tell you about those now. The locally testable codes of this are quite fancy. They use ideas from expanders, they use ideas from that are related to the polynomial codes that I will talk about. But yes.
For LDCs, can you have the number of queries be constant if the rate is bad?
Yes, you can. Yes, the number of queries can be constant. Wait, I'm sorry. I feel like I said something wrong.
Yeah, because you didn't say anything about rate here.
Right. Yeah. So this is no for rate being omega 1. You need the number of queries to be log n. Rate. So then you don't call it rate. N equals 2 to the 2 to the square root log k. If you remember, k is the dimension of the code, n is the length of the code, and queries is auto. So these are the two settings which we do know. Oh, so this is a lower bound that we know. This is an upper bound. So I don't know why I'm mixing these. Okay, we have very few lower bounds for locally decodable codes. Yes. Okay, so should I write that? Okay. So the answer to this is no. Good rate, you cannot have constant number of queries. And then I will tell you the two positive results that we don't know. Yes, that's good. LDCs. So there are two positive results. One of them is queries is order 1, and n equals 2 to the 2 to the square root log k. And if you check, this is less than 2 to the 2 to the log k, which is exponential in k. So it's not bad. And there's another setting where queries is 2 to the root log k, and n is 1 plus epsilon. Yeah, so there are lots of square root logs, 2 to the square root logs for some reason, which are totally unrelated. And there are various positive results on locally decodable codes. These are called matching vector codes. These are called multiplicity codes, along with some expander amplification. Okay. Those are the positive results for locally decodable codes. And neither of these have. I guess there is polylog runtime for this example. Okay. Good. So I will now give you the first example of a very nice locally decodable gate. It is the original one that was. I think the correct reference for this is BFLS, Babai Fortnau Levin Segedi, and it was in the middle of some PCP constructions. They noticed that here is a very nice problem that gets solved. Okay, so these are multivariate polynomial codes. Okay, so we have Q, which is a prime power. So we have FQ, the finite field. We have a parameter D, which is going to equal 1 minus delta times Q. This is the degree parameter. And we have a variable m, which is the number of variables. This is m variate polynomials of degree at most d. Just like Reed-Solomon codes were 1 variate polynomials of degree at most d, These are m-variate polynomials. But we have the additional caveat that the evaluation domain is chosen to be fq to the m, all of it. You cannot take less because then you don't get these local properties. In Reed-Solomon codes, the evaluation domain didn't matter, it was just any set of endpoints. Now the choice matters. And so the evaluation domain is fq to the m. Okay, and now the code is, we will take polynomials of degree at most d in m variables evaluated on all of fq to the m. This is p of alpha, where alpha is this vector in fq to the m, where p of x1 up to xm is a polynomial with degree at most d. That's the code. What's the dimension? First, what's the length? I mean, we already need. N is equal to, what's the length? Q to the n. What's the dimension? We're viewing it as a linear space of polynomials. Each one of them gives you this vector of length q to the m. So it's the number of coefficients in polynomials of degree at most m in d variables. Yeah, this is d plus m choose m. I know this one by heart. D plus m choose m. This is the number of monomials of degree at most d in m variables. This is total degree d. I need to say this, total degree. What's the distance? It is the maximum number of non-zeros that a polynomial of degree d can have on fq to the n. It is number of non-zeros. Yeah. So this follows from the fact that any polynomial of low degree, if it's non-zero, is unlikely to evaluate to 0. So this is called the Schwarz-Zippel lemma. You must have seen it in some places. Schwarz with a T, Zippel lemma. And it says that probability over a random alpha in fq to the m, that p of alpha equals 0, is at most d over q, where p is degree d. Degree of p is at most d and p is non-zero. And this fact, when you plug it in with my nice setting of d, gives you that the distance of the code is delta. So distance, which is no longer d by the way, because we had to use the letter, remember. Distance is delta, and the relative distance is thus delta. Okay, great. So this is our multivariate polynomial. And the asymptotics that I want to look at are delta constant. I definitely want delta constant. And then, how do we do this? Let's think of q huge and m constant or m very small. Q huge and m small. That's a good way to think about it. So q huge, m small. For example, m equals 10. That's not a bad setting. And q is thus n to the 1/10. Okay, but in PCP settings, m goes up to, a very typical setting that they use is q being log n and m being log n over log n. So m is still less than q, but so m can become super constant depending on the application. But we always have constant distance, and the distance in this case is delta. And the delta need not be a small delta, it could be 0.8. Yeah?
Have you replaced this with the construction you did yesterday where you concatenated Reed-Solomon with the binary force code? Would you still also get a positive rate, positive distance code?
Oh, good question. So far, we have not checked that this has positive rate. But if this has positive rate, if you take any positive rate code over a big alphabet and you concatenate down with a brute force code, you will get a positive rate, positive distance code. This does have positive rate in some settings. We will see that in a second actually, which are the settings where it gives positive rate. So let's see what the rate is. So the rate is thus k over n, right? This is d plus m choose m over q to the m. Okay, now I'm using my thing that m is small and q is large. So d is like constant fraction of q. So this is d is also large, m is small. So d plus m choose m is d to the m over m factorial. Yeah, so this is like the d plus m is basically d, and d choose m is basically d to the m over m factorial, and so d to the m over m factorial divided by q to the m. And this calculation, for example, is correct when m is 10. And this is d is 1 minus delta times q, so this is 1 minus delta to the m over m factorial. So is this good rate? Well, if m is constant. If m is constant, this is positive. Okay, so you can take this code with m being constant. It has a big advantage, no, not big advantage. It has an advantage over Reed-Solomon codes. What is the one advantage it has over Reed-Solomon codes?
It's locally.
Oh yeah, we don't know that yet. We don't know that yet. Okay, so what is the other advantage over Reed-Solomon codes? Is there any way?
Much smaller for the same rate and distance. You can give it smaller alphabets.
So actually, it's not the same rate and distance. It's not the same rate and distance, but it is a smaller alphabet size. So it sacrificed a better rate, right? So let's say m is 2. This is 1 minus delta whole square over 2. So this is something which is always less than half, for example. So it sacrificed some rate for the same distance delta. If you compare with the analogous Reed-Solomon code, you're getting it at alphabet size square root n, while the Reed-Solomon code needed alphabet size n. So it is allowing you to go to smaller alphabet size. On the other hand, there are better ways of going to smaller alphabet size, which is by concatenation. So in the end, this code is no better than Reed-Solomon from the purely cold-hearted rate distance perspective. This is not good. But from this other point of view, it's going to be very good. Okay. Yeah, so in particular, this is always less than 1 over m factorial. So if you want to get good rate, good distance codes out of this, you have to stick to m being constant. And small constant too. Okay. So that's the code. And we have evaluated on fq square. We have some values written down. I fixed m equal to 2 for my picture. We have values written down. Okay, and now local decoding. First, decoding. It's not easy. How do you decode this code? It's polynomial of total degree d. Yeah, so the only way so decoding up to delta over 2 fraction errors. For a long time, the only way known how to do this was, some very heavy duty finite field algebraic tricks. So you take fq square and you relate it to fq square, and you do some heavy duty algebraic tricks. Only more recently, there have been more down to earth approaches to decoding this to half the minimum distance. But the rough principle for decoding this is, these are multivariate polynomials. You can restrict to a line like this, and on this you expect to see a univariate polynomial. You can restrict to a line like this. On this you expect to see a univariate polynomial. Right? This is fq cross fq, so you can set. You can consider p of alpha 1 comma y, or p of alpha x comma alpha 2. For some fixed constants alpha 1 and alpha 2, and you get univariate polynomials of degree d, and you can use this and Reed-Solomon decoding as an ingredient and do stuff. Okay, so the local decoding, and this is where the choice of evaluation domain was very good, is based on the following fact, which is that there are also lines like this. So fq square has many lines in it. And what's a line? So a line is a set L of the form alpha, which is a vector, plus beta times t, where t varies in FQ, where alpha and beta are in FQ to the n. And how does that look? Let's take a fixed point alpha and go in direction beta and keep taking multiples of that. And everything is in algebra over FQ, so this gives you q different points if beta is non-zero. So size of L is q, maybe this I can call L alpha beta, and size of L alpha beta is q if beta is non-zero. Okay, so the presence of these lines, these low dimensional sets, where you expect to see something reasonable, is what makes local decoding possible. In Reed-Solomon codes, there is no hope for local decoding. Why is there no hope for local decoding? Yeah?
The high level of the domain isn't large enough, so you can't do like the same phenomenon doesn't happen. Sort of like
So that by itself is not enough. So even Reed-Solomon codes evaluated to the whole of FQ has no hope for local decoding. Yeah?
Because for any small number of sample points, there is a low degree polynomial that will agree with all of those points.
Right. Reed-Solomon codes have no local constraints at all. Take any, if it's polynomials of degree d, if you take any less than d points, and whatever values you see there, that is consistent with some polynomial. So it's there's no information. There's hardly any information to be gleaned from. There's no redundancy when you look at small numbers of coordinates at a time. Yeah. So this is expander codes have a lot of redundancy. There are small subsets of coordinates where you can test for some whether something good happened or not. There are small relations that this coordinate plus this coordinate should equal this coordinate. If there's a constraint connected to those three coordinates, you know that this plus this should equal this. So there's some hope for local decoding in that sense. Okay. So these
are they locally decoded?
Expander codes, all of them, no. Most of them, in fact, no. But one of them is, and that's the one from tomorrow's lecture from Ligius James. In fact, most of them are not. That's
there's a proof that
there's a proof that most of them are not. Yeah.
So are locally decodable codes stronger than locally testable? Like every locally decodable code is also locally testable?
No, there is no connection in either direction. Right. There's a big difference. The big difference is in locally decodable codes, you have a promise that the received word you're touching is close to the code. In locally testable codes, it's you have to check whether that promise is satisfied. So, and the hard part of locally testable codes is to handle those strings that are extremely far from the code. And so the kinds of tools that go into studying them are quite different.
But you're saying that the construction from tomorrow is both locally testable?
No, it's not locally decodable.
It's not?
Okay. Did I say that?
Sorry.
Oh yeah, I hope it did. Oh yeah. Yes.
Do you want to mention VLTCs?
You mean relax?
No, vicinity locally testable codes.
I don't know.
Weren't you at CCC?
I didn't attend every talk.
Oh, okay. It's just an LTC where you relax it to where you only need to test it if
yes. Oh, I know VLTCs. Yes. Oh, that's really nice. Yes. This is these get fed into relaxed locally decodable codes. Yes. Okay, good.
So are there codes which are both LTC and LTC?
Yes, there are. But these are not in the constant query regime. They are only known in the very high query regime. Read these codes that I'm talking about, multivariate polynomial codes. These are examples. These are the original example of both LDCs and LTCs. But then once people defined LDCs and LTCs, things branched out.
So there's no settings where these are pseudo-random objects.
These are not pseudo-random objects at all. Yeah. So that's another way in which suddenly things became very specialized, because when you're talking about just error correcting codes, it's pseudo-random. you expect wherever you go, you expect to see them. But locally decoding and local testing, when it happens, you know it's something special is happening. Okay. So here is the local decoder for these codes. So these codes are sometimes called read-muller codes. I'm going to call them read-muller for now. Read RM. So local decoder for RM codes. And it actually, to be honest, it's a local corrector. To make it a local decoder, I have to specify an encoding map, and there are ways of the encoding map can be such that the message that you write is written on certain elements of FQ square, and one just low degree extends it to the rest of FQ square. So, but I'm not discussing it. So what's the problem? So we are given R, which is a map from FQ to the M to FQ, such that the distance of R from some true polynomial P is at most delta over, let's say, 10, where P of x1 up to xm has degree at most d. And now our decoder is given alpha. So I guess it's given alpha, and oracle access to R should output P of alpha. That's what the problem definition is. Right? We are given access to R. R we know is close to some P, and we want to find P of alpha, not R of alpha. R of alpha is easy. Okay, and here is the algorithm. Pick a random line through alpha. Pick random beta in FQ to the M, I guess maybe without 0. Consider L alpha beta, which is that line, alpha plus beta t in FQ. We will query R on that line. Get R restricted to L alpha. And it should agree. It should. The should is in case there were no errors. Agree with P restricted to L alpha beta, which is the same as P of alpha plus beta t I guess as t varies. So these are evaluations of this polynomial of total degree d at these points on the line. And this is where the total degree is making a difference, because when you take a polynomial of total degree d, the monomials, I mean, even if you substitute in an affine linear form, no monomial that you get after you do the multiplications will be of degree greater than d. Okay, so if you define h of t to be p of alpha plus beta t, capital T is the formal variable, and this is now just a polynomial in FQ with a single variable t, then we should have seen corrupted version of h. Okay, so this is a corrupted Reed-Solomon code word. I mean, I guess the corrupted RS code word, Reed-Solomon code word. Okay. And if we truly got a corrupted Reed-Solomon code word of H, this is something we can use last time's algorithm and decode, and then we get the true polynomial H. If we get the true polynomial H, then H of 0 is P of alpha. So decode using the Berlekamp-Welch decoder and output H of 0. So this is the algorithm. So this it should was just commentary. But what were we doing? We took R restricted to L alpha beta and viewed it as a received word for Reed-Solomon codes and decoded that to the nearest code word. Okay, so I need to prove something. I need to prove that if the total number of errors is at most delta over 10, then this algorithm is likely to succeed. So let me prove that. Here was our FQ to the M. This was our point alpha. There are some errors sitting out there. We have picked a random line through alpha. Since there are few errors and the lines partition the whole space, it's unlikely that you get a line which has more than delta over 2 errors. Right? This is Markov's inequality. The average number of errors on a line is delta over 10. So the probability that the number of errors is more than delta over 2 is less than 1/5. Yeah. So this is the analysis, which is this one line. So the probability that number of errors on L alpha beta is greater than delta over 2 times Q is at most 1/5. Oh, did I need to succeed with probability 0.99 or something? I don't remember. Okay, we'll repeat if needed. So good. So if this happens, if this doesn't happen, we recover H, which is P of alpha plus beta t correctly, and H of 0 is P of alpha is correct. Okay, so this is it was very simple. Questions?
Why didn't we use a constant beta?
Why didn't we use a fixed beta each time? Because the errors have to handle any error pattern. Maybe the errors were on this line.
Okay.
Then that particular alpha will not be decoded correctly. I want to get it right for every alpha. So the randomness of beta helps me dodge whatever the error pattern. This does delta over 10. This delta over 10 can be made delta over. Can I make it delta over 2?
I think additionally you substitute a moment bound, you can use Chebyshev.
Yeah, but you can't use Chebyshev with just a single point alpha. These lines are just uniformly covering. Then there's no pairwise independence. There's only one wise independence. So this can give you delta over 4 maybe. To make it delta over 2, there are ways. But okay, how are we doing? We have 5 more minutes. I will tell you about the local tester for this code. The local tester for this code is very simple. Pick a random line and check that what you see on that line is a read-Solomon code rule. That's much harder to analyze. Yeah. So I'm not going to do it, but that is much harder to analyze. Any questions? Yeah.
And in the range of parameters that we specified, this is locality like n to the 110.
This is n to the
N
110.
epsilon.
Right. This is n to the epsilon query complex. That's right. And rate 1 over m factorial. So next class, I will give an example of a code which has rate nearly 1 and is also locally decoded. While still having n to the epsilon query complex. And then we will see how to reduce that further. So, okay. Maybe I have 5 minutes. I can define the code. The code is, yeah. So these are called multiplicity codes. They are just like multivariate polynomial codes, except we will evaluate polynomials with multiplicity, which means you take its values and its derivatives. Okay, so it has all these parameters. We have Q, D, M, and S, which is the multiplicity parameter. And a delta, I guess, right? D was 1 minus delta Q, right? And the alphabet for this code, sigma, is FQ to the something. So maybe I have to write it down. M plus S minus 1 choose M. Looks complicated, but it's this is going to contain all higher order derivatives. For example, let's just fix S equal to 1. So we're in 2 variables, M equals 2, S we will choose to be 2, and instead of evaluating P of alpha only, we will write P of alpha dP over dx x1 of P at alpha. No, this is D is the partial, right? Which I say D, but I write partial. Partial P over partial x2. These are the kinds of evaluations that we will look at all the points of FQ to the n. Why were there 3? Because it's 1 plus, there's one derivative in each of the variables x1 and x2. If I looked at S equal to 3, I would have dP by dx, dP by dy, I'm calling it x1, d square p by dx square, d square p by dx dy, d square p by dy square. So there will be 3 extra. And the formula for the total number of those higher order derivatives is this. It's just the same as the number of monomials of degree at most s minus 1 in m variables. So that's why it's the same formula as well. So this is a code over this mega alphabet. But m and s are going to be constants. If m and s are constants, it's FQ to a constant. So it is some so like we from read-Solomon we went to multivariate polynomial read-Muller codes, and we reduced the alphabet size and got some gain supposedly. So we're giving that up. We are now going to take high order derivatives, and then we really pay for this many variables, and we blow the alphabet size back up again. But as we saw already, concatenation lets you forgive too big an errors in alphabet size. So at the very end of all this, when you take a multiplicity code and a read-Muller code and you concatenate both of them down to binary codes, the multiplicity codes you will still end up in front, even though you blow up the alphabet a bit. Okay, so this is the alphabet size. And now I'll say what the code is. I basically told you already, right? So C is the set of all. I will write P less than S of alpha. This is all derivatives of P up to order strictly less than S in all possible combinations of variables yeah, this is overall alpha in fq to the m, where p of x1 up to xm in fq x1 up to xm, degree of p is less than d, less than or equal to d. This is the definition. Have we improved anything? I don't think we've improved anything. Right? So we have q, we have d, which is 1 minus delta times q, we have m. We increase the alphabet size, and the code stayed, and the number of code words stayed the same. This makes things worse. But what we should have done is we should have said, oh, the distance was delta. Actually, maybe there's a better distance. Because we're evaluating more things, there's a chance of better distance. This I can now say, so now I can say a nice fact. So if you have univariate polynomials, p of x in a single variable, then what is the number of alpha in fq, and the degree is d, then the number of alpha in fq such that p of alpha equals 0 and p prime, the derivative of alpha equals 0. What can you say about this?
D over 2, number of candidates D2.
Is at most d over 2. Right? Because whenever this happens, x minus alpha whole square divides p of x. So you get a double root.
Yeah.
And we know that the total number of roots counting multiplicity is at most d. So that's why they're at most d over 2 such thing. So this gave us a better distance bound. So actually there's a better distance bound. That better distance bound means that, yeah. So what happened? We changed the alphabet size and it became a better distance. But our problem wasn't the distance, our problem was the rate. We have a code of rate 1 over m factorial there, and we wanted it to go higher. So to take advantage of this better distance bound, we can now increase the degree. And the degree can now be taken more than q even. It can go up much more. So when we set up multiplicity codes, we will now take d to be 1 minus delta times s times q, which is much more than the degree. It can go up as high as the multiplicity parameter times q. Similarly here, I mean, if you were taking polynomials of degree d, you can go all the way up to 1 minus delta times q times 2, and you will still have distance delta. In univariate multiplicity codes, if you look at polynomials of degree 2 times 1 minus delta times q, that resulting code has distance delta. And the proof of that is exactly this. Univariate multiplicity codes with s equals 2. Okay, good. So this is these are the codes we will see next class. We'll start off with just a simple calculation of the rate, and we'll see that it can approach 1. Then I will state the statement about distance, and and then we will see how. So these will give us quite good locally decodable codes. Then we will see how expanders can mix with these and help make it really good locally decodable codes. Okay, so we'll see that next class.